Hello everyone, in this video we are going to make a spectrum analyzer using ESP32 and ST7920 display module. So we are making a spectrum analyzer. We need to know about FFT. So we have to perform FFT on ESP32. If you want to know how to perform FFT on ESP32, go to my channel 3 battery 1 antenna and see the video number 2, how to perform FFT on ESP32. And to control the ST7920 display, I have already made a video. So if you want to know how to control ST7920, go to my channel and see video number 1, controlling ST7920 GLCD display module with ESP32 without any library. So this is the circuit diagram. This is SPDT switch. This is 100 kilo ohms resistors. Connect here right channel of the aux cable and here the left channel of the aux cable and the grounds of the both left and right channel to ground. If you are using only single mono channel aux cable, then remove this resistor, directly connect your wire channel to in the center of the wire and ground to ground. Means what I mean to say is, if you have only single channel aux cable, directly connect the wire here and ground to ground. If you want to use the microphone module, change the switch position and use the microphone module. Let us look at the code. If you have already watched my video number 1 and video number 2 posted in 3 battery 1 antenna YouTube channel, it will be easy to understand this code. If you have not watched that videos, please go and watch that video so that the understanding this code will be very easy. in this code you can I have already programmed this in such a way that you can only change this, you have to only change these 3 parameters in order to work in order to use the spectrum analyzer. First thing, number of samples. Number of samples, this value of number of samples should be in the power of 2, means implies it should be 2 per n, and the n can be any integer, any positive integer, and the frequency should be less than 12,000. As I tested that sampling frequency of ESP32 will be 0 to 12,000, so it should be in between the 0 to 12,000, so I have chosen 10,000. And the noise should be varied according to the, by the trial and error method. You have to upload the code and check whether it is cancelling any noise or not. If it's not cancelling, increase the noise value. Only these three parameters you have to change in this code. And this number of bands is 128 because ST7920 has 128 columns, so number of bands should be 128. And a band for band height is 64 because ST7920 has 64 64 rows, so band height is 64. Another thing which you have to change is, and this one you should uncomment this one and comment this second one. If you want to display a normal graph of spectrum, if you want to display an inverted graph of spectrum, you have to uncomment this one and comment this first if else operation. That's all. Everything is pre-programmed. You will find this code in my comment section or in description. You can copy this code from there. This table is already programmed in such a way that if you change these parameters, if you change these first 3 parameters, the table will be automatically get updated in such a way that you will get a graph in a proper way. Through this if-else operation, the gain will be amplitude will be automatically get adjusted by changing those above 3 values. Let's upload the code and see the output. I am once again telling that this code is written based on the code given in the video 1 and video 2. So if you watch those videos, it will be simple to write your own code again. And I forgot to tell you that the number of samples optimum value is 256. So use 256 for optimum result. You can keep this value as 512 or 1024, any value, but 256 is the optimum value. Compound not connected. Let me connect the board. You can see I have marked 0 to 5 kilohertz on the paper or on the display. 0 hertz, 1.25 kilohertz, 2.5 kilohertz, 3.75 kilohertz, 5 kilohertz. I have only marked from 0 to 5 kilohertz because on the code we have written the sampling frequency as 10,000. So according to Nyquist criteria, we can only reconstruct a signal with the half the frequency. So 10,000 by 2 is 5,000. So we can only reconstruct the signal up to 5,000 kilohertz. So I have marked it 0 to 5 kilohertz. Let's test this spectrum analyzer. I have stopped playing, so nothing is showing on display. When I am playing at 5 kilohertz, You can see the spike is showing at 5 kilohertz with little bit noise showing at the left side because my speaker is not producing proper sound at 5 kilohertz on the full volume. Let me reduce a little bit of volume. So you can see the spike is at 5000 hertz. When I am playing at 3.75 kilohertz, the spike is at 3.75 kilohertz. When I am playing the spike at 2.5 kilohertz, the spike is exactly at the center of the display, that is 2.5 kilohertz. When I am playing at 1.25 kilohertz, the spike is at 1.25 kilohertz, which is one-fourth the position of the width. When I am playing 0 hertz, 0 cannot be done. Okay, let me play 10 hertz. So it is showing the spike at 0 hertz. Let me play at 100 hertz so that the spike will shift a little bit to right. So this is 100 hertz. Spike is showing at 100 hertz. So our spectrum analyzer is working properly. Let us see at 1/5 position of width, which is 1000 hertz. The spike will be located at the 1/5 position of the width. Let's play at 2000. The spike is at 2000. I don't know why it's showing a small spike. Let me try increasing the sound a little bit. When I increasing the sound a little bit, it's showing a complete spike at 2000. I have only increased the volume little bit, but it's showing the spike. When I'm reducing, it's not showing a spike. I don't know why is that. Exactly at 2000. This is 3000 hertz. This is 4000 hertz, which is 1/4 the position of the display, and I have already showed 5000 hertz. So let me show 4500. Let me increase the volume little bit. So our spectrum analyzer is working properly. Let me reduce the volume and see again. Yeah, the spike is showing at 4500 hertz even if I reduce the volume. If I am playing at full volume, little bit noise is also producing, so that the left side spikes are noise. Now let us play the square wave. As square wave is a combination of multiple frequencies, so we will see the multiple spikes when we play the square wave.